Hi, grads. My name is Felipe, and I work in the Schaefer Research Group in the Department of Chemistry. Today, I will be talking to you about my electrochemical and computational studies of cerium dipicolinic acid complexes. The story begins at the back end of a nuclear fuel cycle. Nuclear power is great because it is a source of energy that has little to no greenhouse e- emissions. In addition, it can be uh, operated all year round, independent of weather conditions. The the problem comes when we have to take care of the used nuclear fuel. Used nuclear fuel is a complex mixture of many different el- elements that are a product of the fission of uranium-235 and plutonium-239. In this presentation, I will be focusing on the lanthanides. Working with the lanthanides and the nitric acid media that the used fuel is stored in can be challenging for a variety of reasons. The first is that all of the lanthanides in used fuel exist predominantly in the trivalent oxidation state. So they 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 have similar ionic radii, charge distributions, and solution chemistries. Their bonding in complexes is characterized by mainly ionic contributions. In addition, their redox potentials are typically outside of the water oxidation potential window, which makes them especially challenging to differentiate in the nitric acid media that they are stored in 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 the used fuel. The focus of this research is to modulate the redox po- po- potentials of different lanthanides and actinides by complexation to an appropriate ligand and functional functionalization of that ligand with different electron donating and with drawing groups, which has been shown to be an effective method for modulating the redox potentials of transition metals. Dipicolinic acid is a great choice because it is stable toward degradation in acidic conditions. It has also been suggested for separation of lanthanides from actinides in used nuclear fuel, and there are a variety of derivatives of dipicolinic acid that have been reported in the literature. On the left, I have shown the general structure for a cerium DPA complex. On the right, I have shown a plot of different cyclic voltammograms taken at different scan rates of this cerium DPA complex. The experimentally obtained redox potential for this complex is 0.575 volts in comparison to the 1.2 volts potential of the aquated cerium-3 ion. In addition, what we also see from this plot is that the peak oxidation and reduction potentials do not shift with scan rate, demonstrating the Nernstian behavior of this system. In addition to the thermodynamic data that I presented in the previous slide, I have also collected kinetic data. I use the Randles-Savchuk equation shown on the right to obtain a plot of the peak anodic and cathodic currents versus the square root of the scan rate. What we see is a linear relationship between the peak current and the square root of the scan rate, which is indicative of the redox species being oxidized and reduced in solution as opposed to being adsorbed onto the surface of the electrode, which is what we want to see. We can also see from this plot that the peak anodic and peak cathodic currents match up well, which demonstrates the fully reversible behavior of this system. In addition to the scan rate dependency, I was able to extract a diffusion coefficient, which is a measure of the mass transfer of the complex and solution to the surface of the electrode. The diffusion coefficients that I derived from the anodic and cathodic peak currents are nearly identical, which is a further indication of the fully reversible and Nernstian behavior of this system. I complemented the electrochemical data that I obtained with density functional theory computations. From these computations, I can gather information about the energies of the molecular orbitals in the complexes, and about the contributions of the cerium valence 4f or orbitals to the molecular orbitals of the complex. Specifically, I want to see how complexation to to DPA and the functionalization of DPA uh, uh, affects the properties of the highest occupied molecular orbital and the lowest unoccupied molecular orbital. I want to look at these parameters specifically because we can think about the uh, electron transfer from the surface of an electrode to a redox active species in solution to the increase or the decrease of the energy of the electrons at the surface of the ele electrode relative to the energies of the HOMO and the LUMO of the redox active species in solution. For comparison, I I was able to find an experimentally obtained redox po potential for a cerium DPA complex that was functionalized with an amine group at the 4' position. And what I found what was that for the cerium-3 oxidation state, the 4F char 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 character li lies exclusively in the HOMO of the cerium DPA complexes. Most importantly, what I found was that the functionalization with the amine group raised the energy of the HOMO relative to that of the parent DPA complex, which explains the 600 millivolt shift in comparison to the aqua cerium-3 ion of the parent DPA complex and the 1 volt shift of the emanated DPA complex relative to that of the parent DPA complex. I went on to do the same kind of analysis for the cerium-4 complexes, which are the oxidized form of the cerium-3 DPA complexes. And unexpectedly, what I found was that the emanated DPA also raised the energy of the LUMO above that of the parent DPA complex, when I would have expected that Since the aminated DPA it increase the energy of the HOMO in the cerium 3 co- 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 complex, I would have expected that it would have de- decreased the energy of the LUMO in comparison to that of the parent DPA complex. In conclusion, co- co- complexation to DPA stabilizes cerium 4 and brings the cerium 3 oxidation potential into the window for 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 that of the nitric acid media in spent fuel, as shown by the 600 millivolt cathodic shift uh, of the cerium 3 aqua oxidation potential. This is due to the increase in energy of the 4f orbitals in cerium imparted by the complexation of DPA. Furthermore, the functionalization of DPA with an electron donating amine group at the 4' position of each DPA further helps to stabilize the cerium 4 oxidation state, as shown by the 1 volts cathodic shift of the aqua cerium 3 oxidation potential. This is due to the increase in energy that the aminated DPA imparts on the cerium 4f orbitals in comparison to that of the parent DPA complex. I would like to thank all the members of the Schaefer Research Group for all of the guidance and assistance that they have provided me with. Thank you all for listening.